I'm so excited to be here. I absolutely loved the morning talks. They were very stimulating, and hopefully you'll find my work just as exciting. So my work is going to take sort of a slightly different approach. Hopefully it'll add to the diversity of things you've been hearing through the day. What I think about is, so much of my work in the last 6, 7, 8 years has been on, as we are going to get increasingly more and more amounts of data through wearables, through electronic health records, what Lee really calls dynamic data cloud, so I took that term from him, where you're tracking individuals over time. In this case, this is an infant just born. Just from the time they're born, you have all this data that's getting collected in the NICU, and as they grow up and they're visiting the hospital or the outpatient clinic, we're repeatedly collecting measurements. And 8, 9, 10 years ago, this wasn't possible, because what we would have to do is to design prospectively an experiment. And in this experiment, we would have to determine upfront what are the 5, 6, or 7 measurements we'd make, and then we'd write an NIH R01. And then they'd pay us to enroll, and it would take us forever to get to the time when we could enroll. We could only enroll 500 or 600 people at most, and follow them up for a very short period of time. And what really this enables is this beautiful possibility of being able to take large amounts of data and start to think about how do we model individuals and model populations of individuals and understand disease in great levels of detail. And it's not the be-all, end-all, but it's an amazing starting point. And this is some of the stuff that I will talk about today. So let me give you a concrete example. So here I'm talking about scleroderma. Scleroderma is an autoimmune disease. It's basically a disease where essentially your skin thickens, and it thickens because of fibrosis. It's a systemic disease, so it affects many, and so also forgive me, I am by training not a biologist, I'm a computer scientist and a statistician. So everything that I'm saying related to the disease is really things I've learned from interacting with incredible collaborators. So in this particular case, this is a disease where it's systemic in nature. It affects many parts of your body, many different organ systems. And the challenge here is that the way it affects different individuals varies a great deal. So in some individuals, it really affects the lung function. Effectively, they'll experience lung decline very quickly, and it becomes the main source of morbidity, sometimes often leading to mortality. In other cases, the lung function is completely fine, but much of the impact of the disease is just on the skin or the kidneys or the GI. And the challenging part of this disease is when we think of guidelines. Guidelines typically think about, one particular complication, what do we do? But in this particular case, when we're looking at scleroderma experts, and Hopkins is one of the largest centers in scleroderma nationally, even though they see scleroderma patients all day long, the challenge is you want to know for this individual, what is their likely course going to be? Who is this person? Is this the kind of person for whom we'll experience major lung decline or major kidney decline? And if I could think about that, then I could start to manage them more, tailor their therapies more effectively. Of course, as a computer scientist, I think a lot about ideas that have the ability to scale. And in this particular case, the ideas that I'm talking to you about, I'll describe them. One thing I want you to think about is like the principles of what I'm describing. And the principles of what I'm describing are very much targeted at this idea of how do we model diversity? How do we think about leveraging data to learn about diversity? And while scleroderma is one such disease, I don't have to really speak to this audience because this is so natural to you, where you don't really see disease as one disease. It's really sort of, many faces to a single disease. The question is, how do we think about, the individual in the context of this very diverse population? So making it more concrete, in scleroderma, for instance, here are the kinds of questions they want to ask. Here, PFVC is the percent of forced vital capacity. It's a lung marker. They measure this in order to track lung function. This is one of the key markers that are measured. It's very easy to measure, so it has this convenience. You don't have to do any sort of invasive tests. And it's a very, very useful marker. If PFVC is declining, this person is at risk of their lung is deteriorating. If PFVC is high, the person's doing healthy. And the questions they tend to ask are, here in this individual, I'm showing you on the x-axis time in years, and this is time since first symptom. And the question is like, all right, I've seen them in 4 visits. You have a lot of other data about these people, so I'm not going to try to plot all of it on one slide. But what they're fundamentally looking to do is, okay, given everything I know about this person, where is this person going? Are they going to be flat? Are they going to decline? And as they see more data, in this particular case, you might have thought, maybe they're trying to flatten. And as you see more, actually, it turns out that was transient. Really, they may be likely on a downward decline, still not very sure. And so if there was a way to get a more granular view of what was going to happen, they could now start to tailor drugs more effectively. Now, I spoke about scleroderma as one disease, just in order to show and discuss the diversity of ways in which I think these ideas are applicable. I'm going to talk about a totally different condition, and this is sepsis. And so sepsis is something where my lab has done a lot of work. Sepsis is one of the leading causes of death. It is a host negative inflammatory response to infection. It's a place where what's exciting is that while we don't know how to treat in the late stages very well, if you can get to the individual quickly enough, existing therapies are often very effective. Part of the challenge here is clinically, often our current protocols don't recognize sepsis until it's pretty late. So people have tried to do all these, people have tried to develop biomarkers in order to sample the blood and try to find genetic markers that are indicative of suspicion of sepsis. Part of the problem is all of that requires the clinician to suspect sepsis and then go do something to measure it and then go sequence it and come up with an assessment. So here again, the question is, there's all these hundreds of markers that are collected, and sepsis is again very challenging because depending on the location of sepsis, like where exactly it's occurring, depending on this person's comorbidities, for instance, do they historically have history of COPD? Do they have history of chronic kidney disease? It can look very different. And again, this diversity is key. And the question is, how do we leverage, build these N of 1 models? Okay? So before I go there, this is inspiration from William Osler, who's one of the founding fathers of medicine, also one of the founding fathers of medicine at Hopkins. And he says, variability is the law of life, so no 2 faces are the same, so no 2 bodies are alike, no 2 individuals react alike. And really, embracing this wholeheartedly is where I think the future of health is. So the central question here is, how do we build these N of 1 models? Okay? So you have here, every circle here, you can imagine as an individual, they have attached them these dynamic data clouds. And the question is, one way we want to think about this is, what can I borrow from other individuals to say something about this individual? So I apologize up front, because my talk is going to get a little statistical and a little technical, but that's OK, because I have enough pictures to go along with it. And I at least hope you'll walk away with some high-level ideas that you'll enjoy and like thinking about. So at a super high level, what am I after? I'm trying to create a mathematical and computational language for modeling and learning about different sources of diversity. Right? What I would like to do is to use data in order to uncover these sources of diversity and layer these different sources of diversity in order to construct these N of 1 models precisely. Okay? The second thing I would like to do, and this is especially important for people in the audience who are very excited about or maybe sick of the New York Times articles that talk about machine learning day in, day out, is the idea that I think at the moment there's an enormous amount of euphoria around these kind of black box models you can just deploy on some data set and out come some answers. But I think in health, we really have to think about the fact that we have so many different data sources, and they each are uncertain to different extents. They're messy, and they have different sources of bias, and they have different sources of noise. So if we want to build precise things in health, then we'll have to do something called uncertainty quantification, not so surprisingly, right? So we have to think about, what are the sources of information? What are the sources of noise associated with, integrated in a principled fashion, and come up with something that allows you to do uncertainty quantification? So those are sort of principally what we're after. Okay, so now I'm going to do a slightly deeper dive in the context of scleroderma. And this being a model, and will hopefully, you'll see how this could perhaps generalize. So here it is an example. We're always going to be referring to these kinds of markers. In sepsis, you have hundreds of these markers. In scleroderma, you have 20 or 30 of these markers. And what these markers represent are continuous valued functions. You measure them here, in this case, at every visit. And we're going to try to model these trajectories. Okay? And so in scleroderma, you get many, many such markers. For instance, you have something to measure skin function. They measure the skin thickness at different parts of the body, and they use that to measure skin progression. They have some ways to measure lung function, vasculature function, heart function, and so on and so forth. And again, different markers are precise to different extents. They're informative about different aspects of health, and they may have redundant information. The other aspects of this is note, unlike an experimental data set, this is a non-experimental data set, which means you don't have control over when you get to sample. People come in when they come in, and you have to think about the fact that they're going to come in when they're going to come in. Now, I can't solve all the problems right now. I want to motivate some of these problems. I'm not going to solve all of them today, but what I'm trying to do partially is to say, but these are things we can think about. These are missing data assumptions we can incorporate and reason about in trying to do uncertainty quantification. Okay, and here in this particular case, I layer on a whole bunch of individuals and talk about diversity. Here you're looking at, 120, so when people are at like about 30 or 40, 50 even sometimes, they're at like great risk of death. And so in the population, there's tremendous diversity in terms of what typical profiles of individuals look like. And this is data over 15 years for 4 different markers that I'm showing, okay? There also isn't you'd expect the happy state where you take all these people and maybe you see groups, right? And if you could see groups, your life would be simplified. So it's not quite as simple as that. And the point is there's still hope. We can still find structure. All right. So the first thing people often do when they have a ton of different types of data, they say, well, I can just go ahead and cluster them, right? That is kind of like the 101 we learn. And so when we cluster them, what do? We say something like nearest neighbor. So I'm going to take a whole bunch of data. I form a massive vector. In this vector, every element is some way for me to summarize some aspect of the thing you have, your lung function, your heart function, et cetera. I take all this trajectory data, I somehow quantify it into features, I make a massive vector list. And now I take the entire population and I run what's called k-means, or some variant of that, right? Some variant of nearest neighbor. The challenge is when you layer in many, many, many different kinds of data, when you're fundamentally doing clustering, you're assuming you understand the notion of distance. You understand how to take 2 vectors and measure distances between them, which means you're saying you understand how 2 units of separation in PFVC compares to 5 units of separation in RVSP, and 1.5 units of separation in a totally different measurement. Right? Now imagine when your measurements are messy and you don't I don't know, maybe nearness in PFVC is more important than nearness in PFVC, in skin function, or nearness in heart function. So this notion of just this is predominantly, I often review papers for subtyping, this is predominantly the method people take, which is they take all the data, and they turn it into a massive vector, and they do some kind of clustering, and then effectively you get some clusters, and we do some gene analysis, GWAS study against it. We find some incidental, gene associations, and we declare that, victory, right? So you can't do that, is basically one takeaway I want you to see. So next time you're tempted to do that, stop and question yourself. Okay, so moving on, so you can't quite do that. What you have to do is to think about these various sources of noise that may be perturbing the measurement, and the fact that you don't actually know how to compare distances across different dimensions. And so you're going to have to be a little bit more clever about that. Okay, so the second thing that people often do is more in the setting where you say, all right, I'm not going to care about clustering to find clusters and then predict a given individual's measurements by just finding the closest cluster. Instead, what I'm just going to do is to train a predictive model, right? I'm going to take my favorite method, machine learning method, or whatever regression method, and here's it is, right? So in this particular case, I have my data, right? So this is my PFEC data, and I have all sorts of other data. And then I have, data 5 years out, 10 years out. I want to be able to predict, because that's what Dr. Wrigley needs. He needs a way to know what is it going to look like in 5 years or 10 years, and I train my favorite regression function based on what it is, right? So you can do that. That's what state-of-the-art methods do, which is great. But here's the issue, which is you don't know how to compute features when you have crazy data of this sort, because it's possible that somebody who has 15 measurements will have far more reliable features than someone who has 1 measurement, right? So collapsing it is not so obvious. The second and more interesting and unintuitive thought is the following, that when you're doing this, what you effectively are doing is explaining away variability across individuals based on the observed features alone, right? When you're doing something of this form, you're hoping all the differences across individuals, I can explain it away using all the other covariates, risk factors I've seen effectively, right? That's basically what you're trying to do. And the key insight here is that in health, often many sources of variations exist that we haven't known to measure yet. We don't even know about them yet, right? So the question is, can we still exploit them? So this is my graduate student, Peter Shulam. He's been working with me for 3.5 years on this and has done some really exciting work. So I'm going to tell you a little bit about some of the ideas here today. So for instance, so let me give you an example. So let's imagine these are 3 sets of people, okay? And based on all of the data I'd observed about them, I managed to separate them into clusters A, B, and C, because I had enough to separate them out into these 3 groups. But if I actually, if you look more carefully, within each group, you can see there's still differences, right? This is an example of the shades of scleroderma you haven't discovered yet, or the shades of autism you haven't discovered yet, or the shades of asthma you haven't discovered yet, right? So there are factors that could potentially have explained them, we just haven't known to measure them yet, right? So based on the observed factors alone, I can get this separation, but I can't get this micro-separation here. Now here's the key insight. If I had known what was the source of variation, obviously, I could just go ahead and measure it, and hello, my job would be done. So why am I telling you this? This seems pretty obvious. The question is, I'm going to try to be a little bit more clever than that. So here's the clever. So what I'm going to show you here is 4 individuals. In these 4 individuals, I take all of the other measurements. I'm taking 4 individuals here that have very similar values for all of the risk factors that are observed, okay? And now, this is scleroderma, okay? So now I'm looking at the PFVC marker, and I'm looking at the residuals, okay? So these people have very similar values here, and I'm looking at the residuals. And when I look at the residuals, what I see is, here are individuals who are declining and then stabilize in the PFVC value. Here are individuals who are sort of getting better, right, over time. So again, I hadn't known to measure, like all I've done is I'm taking the trajectories, I'm trying to model their trajectories. I did regression on the trajectory value data using all of the other markers I had known. I did regression, I looked at the residuals, and then turns out there's structure in the residuals, and the structure of the find that there are people who have this form of trajectory, and there are other people who have this kind of trajectory. Now, you might say, well, maybe this trajectory is because this person has gene 1, and this trajectory is because this person has gene 2. Now, if you had known about it, you would go measure it, and you'd be done. But you don't know about it. But what do know? You do know the fact that if I look at the residuals, I take my population. This is where the population comes to bear in the N of 1 models. If I go to my population and I cluster them, I can uncover this kind of group structure. As soon as I uncover this group structure, this kind of becomes like a feature. And all you have to do is infer it. If I saw partial data, right, you could imagine on this individual, if I told you this feature is associated with gene 1, and if I showed you partial data, you can kind of see this part, and if you only knew that these were the 2 groups, you would have inferred it, that it's likely group 1. In other words, it's likely, quote, imaginary gene 1, right? So I suddenly was able to uncover this latent feature that I didn't actually observe, but somehow can leverage in improving my N of 1 models by taking population data into account. Okay, so I can take this a step further. Let's even look at people within the same group. If I look at people within the same group, let's imagine this is my brother and this is me. He ate a lot of cheeseburgers, so his lung function is way worse than mine. And as a result, as I see more data, I can not only infer that we are both in this group, I can also infer that I am just a little bit healthier than him. That's not entirely true, but for today it is. So what this means is I was able to learn another repeated measurement about this individual. Again, this is another what I call a latent factor. It's a feature I never got to measure. It's an example of, let's say if I was a chronic smoker. I never knew to measure it ahead of time, but I can sort of uncover it by looking at these residuals. So effectively, what does this mean? I can account for heterogeneity in disease scores not just due to observed factors, but due to these latent factors. And we can learn these latent factors from data. The second we can learn these latent factors from data, we can basically start to build much more precise models. And I will convince you by the end of the talk that is the case. So in this case, the next little piece you also have to think about is the fact that, we often work with these super discrete models, but health is continuous. I'm continuously evolving in health. My health trajectory is continuously changing. And so here in this particular case, when you look at individuals, you don't have measurements nicely at specific points, so you can afford to measure things at very specific points. You really have to think of health as a function over time. And what I'm doing here is I'm taking advantage of stochastic processes, which is just a framework for thinking of health as a noisy function, right? So just for a second, humor me, which is what I'm doing here is saying, if I had data at these 5 points, I can get a distribution of what the value would have been at all the other points, which means it allows me to naturally represent uncertainty over what we think the values will be when I don't get to measure it, right? So that's basically what I want. So now using this framework of stochastic processes and the notion of latent variable models, which are these latent factors I uncover, I can effectively learn these functions that allow me to capture diversity across individuals really nicely, okay? All right, so now I'm gonna do in like a few quick minutes how to put it together, but don't worry about the details if it doesn't make sense at a high level. So at a high level, what we're doing is basically representing, I said I want a language, right? I want a language in which I can compose these models. So here's my language composing these models, which is, I have these notions of random variables. Random variables represent the value of things at specific times, okay? So here in this case, this is my value of the particular marker. This is the time at which the marker is measured. These are both happen to be measured in this given individual. And now I'll start to layer in random variables that represent specific aspects of health for this individual. And this is me turning the ideas I just described into a mathematical model. And the cool thing is, if I can write down a mathematical model like this, and I can run inference on this, then I can start, the hope is, as you see new diseases, you can just compose these models together by putting these building blocks together, and then off you go to get inferences about health in a new disease. So in this example, I'll continue to build how we think about PFEC, right? So here we have this person's data marker. And I said to you, look, first thing I do is I'm going to regress on all the data I see about this individual. So this is my classic regression. And what it does is gives me a mean trajectory. Now I'm going to layer on top the fact that there are residuals. And when I look at the residuals, they're group structures. So I'm going to layer on top these random variables that capture this group-specific structure. And what this does is basically refines the population-specific trajectory with a group-specific trajectory in order to make it more precise. Third, I continue down this path that individuals, even within a group, can differ a little bit. So I'm going to, again, layer on top some more random variables. And you're thinking, the good news is you're just hooking together pieces. It's a language, right? You're just hooking together pieces. And then when you run inference, it'll figure out the values of these missing random variables. And similarly, here in this particular case, if you have noise of different types, for instance, in Scleroderma, you have transient noise, which could be due to the fact that you may have pneumonia, so your lung function is going to be perturbed for some correlated period of time. You want to have noise models of that sort. You can hook that up. All said and done, this is my model for writing down what this person's lung function looks like for this individual and how it relates to the population and how does it relate to the population. The interesting thing here is that some aspects of this model is inferred across the individual itself. Some aspects are shared across subgroups. Some aspects are shared across the entire population. So we're layering on different amounts of data to learn this, okay? So this could have been a mouthful, but at the end of the day, I want you to think of 2 key ideas. We want to capture diversity. We want to think about latent factors that are causing diversity. We want to think about factors that cause diversity beyond what we could observe, so we can discover them, like in this case, group structure. And we want to be able to learn this from data and model these as uncertain random variables. So I want full uncertainty quantification over it. So now, let me use that model to do some interesting, like show you some interesting ideas in practice. So here in this case, here's an individual where they're coming into the clinic. We have tons of other data about them, like the age and the gender, what autoantibodies they have, what are the other markers like skin function, lung function, GI, kidneys, and so on and so forth. And here, what I'm doing is basically using that model to predict. In this particular case, for instance, she's white, female, 40 years old at onset, has SCL70 positive, super noisy measurements. And what I'm showing you here is in black, all of the measurements that was used by this model to forecast what the likely trajectory would be. And in blue, it's the most likely trajectory. In green, it's the next most likely trajectory. In red, what I'm showing you, the measurements that were in the future, right? So I'm layering it on. And here's an example, right? So this is pretty cool from their point of view. They can see these dense dynamic data clouds playing out in real time, where it does real-time inference and basically makes an assessment of what the likely trajectories are going to be, and based on that, make assessments of what to do next, right? So in this particular case, we think, well, maybe the person will be stable. We see a little bit more data. We think, you know what, very likely to decline. And then at that point, year 4, it starts to become very confident. Very similar example. I'm going to move on. In the interest of time, I have time till 2:30. Is that correct? Or 2:45? I'll keep going till Lilia tells me. So here in this particular example, so here, basically, what I did for you was show you this model. And if I compared this model that I just developed to, say, a population-level model where I didn't consider these other factors, in other words, I didn't consider these latent factors I spoke to you about, what I would see is that basically, so this is my population-level model on top all the way. These are other variants of my model with only some sets of latent factors accounted for, and this is the full model. And effectively, what I'm showing you here is basically having, by taking into account these latent factors, inferring them and taking them into account, you're able to predict far more precisely than if you had just taken into account the observed features alone. Here, we're going to hook together multiples of these models, and now what we can do is some kind of multiple trajectory inference, right? So the docs now can see not just what's happening to the lung, but what's happening to the lung and the skin and the vasculature, GI, all together. So this is doing joint inference on these trajectories in order to figure out what's likely to happen to this individual. I'm going to skip this result. One interesting and exciting application we're exploring is, beyond clinical decision support, is in trials. Right now, trials are often underpowered for diseases like this because they're trying to do all comers. And the question here is, if we could identify, for instance, a specific drug is targeting lung function, a natural question to ask is, can we identify the people who are likely to be declining from lung function? And if so, then we could specifically recruit those types of people. And so this is effectively saying, by using models of this kind, we can identify much, much more quickly who are the people who are likely to be decliners and include them in trials of this kind. And so this is sort of a new application we're exploring. Now, I described to you all in the context of scleroderma, we use these very, very similar techniques. But here, in this case, in the 150-dimensional data set, instead of looking at data, 10, 15, 20 measurements over a period of 15 years, we're looking at 10,000 measurements over a period of 5 days or 10 days. And the application here is of sepsis, which is, sepsis occurs. The question is, can we identify them early? My lab showed very early on, 2 years ago, that, hey, with all the data that are in the inpatient setting, if you were to precisely think about these kinds of data, actually there's hope. Maybe we can identify sepsis early. In fact, we showed, a median time of 25 hours earlier prior to septic shock. For those of you who are not familiar with sepsis, the interesting thing is in sepsis, every hour treatment is delayed, risk of mortality goes up by 7 to 8%. So this, early detection is very exciting. Now, in the last year and a half, what we've done is by basically taking into account, but the issue is that the false alarm rates were still too high. And earlier on, we heard the talk that, obviously we care about antibiotic resistance. We can't be giving antibiotics all willy-nilly. So the previous method does early detection at the same false alarm rate as existing state-of-the-art. But now what we've been able to do is improve true alarm rates by 100 to 200% by taking these kinds of methods into account. So this is really exciting because this is basically an example of a probabilistic reasoning engine building these N of 1 models in the clinic and taking their stream of measurements they're leaving behind in order to do a very precise inference about what's going on. This is now a system we've deployed at Hopkins in the hospital, and we're sort of using it within the workflow, routine care, and it's been very exciting to see. So in the interest of time, I'm going to skip all of these slides. And actually, I'll do one last one. Can I do one last one, Ilya? So here, the other thread that we've started to do is to use these kinds of methods in order to also infer not just things like what their risk trajectory will be, but also what is their likely treatment response. This is very hard to do because this kind of data is very biased. It's high-dimensional. Doctors often give drugs to the people who they suspect to be sick. So you can't treat it like data that's from an RCT. You have to adjust for the fact that there's all sorts of bias in who's getting these medications. And here, in particular, the fact that this is being done repeatedly for all sorts of treatments simultaneously makes this a very hard problem. And so what we've done is we've developed methods by which we can start to get these notion of individualized treatment response. We can see here, in particular, I'm showing you this example where for different medications that are being used to manage blood pressure, at different doses, you can get a sense for what this plot shows you is over time. And on the y-axis is changed in blood pressure. And different medications here show you the degree to which on any given individual it is effective. And so some individuals, for instance, vasopressors are not effective at all. On other individuals, it's very effective. And so this ability to take measurements, infer treatment response on the go allows us to now dynamically tailor, well, let me identify who are the individuals who are going to be responsive, and then give those individuals these kinds of medications. And with that, I think I think electronic health record data provides us numerous opportunities to learn about populations in great levels of detail. Yeah, I think especially some of the things that were spoken about today, if there are opportunities for intersecting them, I think we will learn a lot of things much faster. And with that, thank you.
So in the interest of time, we can maybe take one burning question, but Suchi is going to be back on the stage for the panel discussion, so you can also ask questions at that time. Do you have a question now? Please.
Yes, thanks, Suchi. I'm a Philip Beeser investigative rheumatologist at Providence, and so you picked a particularly difficult disease. It's almost as bad as lupus in terms of modeling.
Yep.
But one of the things I must have missed it because the ideal modeling, it would seem to me, would be based on observing patients in their natural state untreated over time. In order to pull out these latent features without the, since you don't have biomarkers, you don't have genetics to help you. Yet we're jumping in immediately with treatment and trying to ameliorate the different clinical domains that you're deriving your measurements from. So can you explain how you build that into the system?
Yeah. Okay, so the question you asked is, how do I think about the fact that there are all these treatments being given to them, and how does that then affect the actual course of disease you're seeing? Okay, so I'm going to answer this at two levels. So there's the level of what kind of treatments are known in scleroderma and how that impacts long-term disease, which turns out in scleroderma, it's one of the harder diseases where you don't have that many treatments that affect long-term course. But then there's sort of the kind of more generally, how do these techniques become applicable in diseases where you are seeing tons of treatments happening simultaneously, and you have to think about it. So the thing that's interesting is I didn't go into the technical details of this because it was a very short talk. But what we're really doing is you want to build these models that take into account, estimate treatment effect, and take into account treatment effects in order to uncover what the course would have been had the treatments not existed, right? And that's effectively...
That's tough.
Yeah, that's tough, but that's not, but the interesting thing is it's not like we need to give up kind of tough. The interesting thing is there are very principled ways in which you can make assumptions and validate those assumptions clinically and then under a surprisingly broad array of settings, you can actually infer these estimates, right? So effectively, I think the one thing that's happening is we're shifting from like very well-curated data sets where the onus was on the experimentalist to do a great job making sure the data was great. We're kind of moving towards the onus is on the computational scientist to do a rigorous job. You know, basically, we have to go to the gym more often to flex our muscles harder in order to build the right kind of models. And this is what makes it very exciting for us in a way, that we have to like push ourselves a lot harder to think about tricks. But the interesting thing is you can actually prove things. You don't have to believe me, right? Like, we are not sort of going to just do things because we think this is correct. And so in a surprising array of scenarios, and you know, there's a lot of interesting research in causal inference where you can see if certain assumptions are true, which are, you know, you can sort of semi-reason about. You can actually infer these effects, and then you can discount for it and see what the natural progression of trajectories would have been. I also wanted to say, like, I think the interesting thing to me is the convergence, right? I really believe in this idea that it's going to be, you start with the model, it's going to give rise to hypotheses. I didn't get a chance to cover the kinds of interesting hypotheses that have come about. Typical progression trajectories we've discovered that are now leading to, you know, where we've done full sera autoantibody profiling to see what kind of, you know, or maybe there are novel autoimmune markers that are driving this. So I think it's going to be iterative. It won't be, but it'll be a lot faster than if we ignore this data because it's so messy, right?
Thank you.